Hello, class. Today we have Lab 2, and I was thinking what am I going to do with Lab 2 and stuff like that, but I actually put down on the sheet of paper, this is one of my favorite labs to ever give out, and you're probably going to say, hey, what does this have to do with engineering mechanics? Hey, what does anything have to do with engineering mechanics? But this is a fantastic lab. In fact, some of you who have had me before for either engineering 1500 or for network theory may have already had this lab. It's a lab where I try to teach students all about logarithms and about semi-log and log-log graph paper. In fact, I'm going to, while we're doing this, I'm going to try to, in the background, print out a sheet of log-log graph paper. I printed out a sheet of semi-log graph paper, which I have right here, but I thought that I'd print out a page of log-log too, so that I can show you what you are going to have to go and get so that you can do the lab and send it in to me. Now, all the time that I'm talking about this, I want to point out one thing. You know, here, just a second, I will put this down and I will bring up my video for posterity. Yes, I am growing a bad mustache. It won't be here for long, but I just thought that I'd touch base with everybody because I have been doing a lot of these just with the tablet, and I haven't really, switched back into seeing what's going on. And I'm sure that my great-grandchildren are probably watching this, except they've somehow made it into a three-dimensional hologram someplace. Yes. So I'm going to switch back to the other camera now. And I want to show you what we've got. Now, here's what you want to be doing while I'm going through all of this, right? You want to be writing these down. These are two X and Y sets of data that you are going to plot. You're going to plot one on a semi-log sheet of graph paper. That's the Y equals AB to the X, so the exponential relationship. And you're going to plot this one right here on a polynomic or a log-log sheet of graph paper, which gives us the Y equals AX to the B. Now, always remember, it has to plot to a straight line. That is the elephant in the room. All of these, whether it's linear, exponential, or polynomic, all have to plot to a straight line. What you're really doing is you're figuring out what a straight line fit will be for this type of data that's nonlinear. Now, everybody knows that if we have a linear relationship, I'll just make a linear relationship right down here, right? This is linear, and this is linear. So we've got a linear relationship, and we know how to get an equation from that linear relationship because it would just be y equals mx plus b, right? B is your y-intercept, m is the slope of your line, and we all know how to do that. So in a small way, anyone who can do this and is dealing with a linear relationship between two variables can predict the future. Right? They can predict the future. That's right. And that's what you're going to be doing here, but you're not going to be doing it for a linear relationship. You're going to be doing it for a linear, right? Linear x-axis, logarithmic y-axis. And in fact, we're going to be looking at those plots how I would plot on this semi-log sheet of graph paper. That's right, this is semi-log. Semi-log sheet of graph paper, the relationship is y equals ab to the x, right? You know, for instance, maybe it's y equals 7e to the x, right? Wouldn't that be a relationship that you would plot? That's an exponential relationship. In fact, how do I know if it's an exponential or a polynomic relationship? Well, an exponential relationship goes up much faster than a polynomic relationship. An exponential relationship goes up by the exponent, right? As x gets 1, 2, 3, 4, 5. Well, I'll tell you what, x is an exponent here, isn't it? Whereas down here, x is just a variable, and I've just got a constant b. Let's say b is 7. 7. Well, how long is it going to take x to get up to 7? Not long. And then it's going to go up to 1,000,000, isn't it? And that's what we've got here, right? You can see as x goes up in an exponential relationship, y equals ab to the x, it goes up real fast. Now, what I've got here, right in the center, is I have the NASDAQ, right? The NASDAQ return. You're probably saying, oh yeah, NASDAQ, that would be an exponential relationship, Professor Grenquist, because everybody knows that the NASDAQ is a percentage-based index. So obviously any percentage-based index has to be an exponential relationship. Anybody would know that. And that's right. That's what I say too. That's right. Everybody knows that an index-based, percentile-based relationship is going to be an exponential relationship, and we can figure out what that is. So I've got two things here, because we've got to find out what, if it's y equals ab to the x, how do I find a and b? Those are two constants, aren't they? Well, if it actually plots to a straight line, if it plots to a straight line, and I'm looking at the NASDAQ, now I'm going to share a screen with you, right? I'm looking at the NASDAQ between 1976 and 1995. You're probably saying, yeah, that's not a straight line. Of course it's not. It's because it's a linear y-axis that I've got right here, and it's a linear x-axis that I've got right here, isn't it? Right? But what happens when, instead of looking at it in just regular linear view, I turn it into semi-logarithmic plot? Right now, look at the x-axis. Isn't the x-axis still from 1976 all the way up to 1996, all separately spaced along here? Does everyone see that? But look at my y-axis now. My y-axis is in a logarithmic projection. And I think you can see what I mean. Look at that line. From 1976 all the way up to 1996, you had almost a perfectly, I mean, it's not a perfect straight line by any stretch of the imagination, but we could lay a ruler along that, and that would be a pretty straight line, wouldn't it? That's right. So what I did was I took values off this. I'm just going to stop the sharing right now. I took values off this, and what I got were these values between the year 1976 and 1995. Now let's just plot some of those values, but we're going to plot those values on our semi-logarithmic graph paper, right? I'm going to have to push it up there a little bit so that you can see what I've got here. But now, how am I going to plot those? Well, it's pretty easy along the x-axis, isn't it? I've gone from 0 up to 14, right? So I can go from 1976 up until 14 years later. I guess that's 1990. So what I want to do, though, is I want to plot these on this logarithmic paper. So how does logarithmic paper work? Well, let's look at our range. Now, if I'm looking here, I'm going from 80 all the way up to 750. So that means that the first decade on here is going to be from 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, right? Does everyone see how that goes? And then the next one up here would be 200, 300, 400, all the way up to 1,000. So my y-axis starts at 10 and it goes up to 1,000. Does everyone see how that works? Now, it doesn't matter. It can never get down to 0, a logarithmic axis, can it? Because I could start at 1. I could start at 0.1. I could start at 0.001 and then go up each decade, right? But I haven't. So let's start plotting a couple of these. Well, the first one we have is 80. Well, let's go all the way up to 80. That would be right about there, wouldn't it? 80. And then at number 1, it's at 100. So there's 100 right there. Number 2, well, let's look at number 2 is 110. So that's not far off 100. That would be, well, if this is 200, that would be 125. So this must be 115. Did I say 115? 110. So right about there. Well, that's not very indicative, probably. And then at number 3, I've got 125. So I'm going to go up to 125, which is right there. Let's go up to 5 and see what 5 is. Well, 5 is at 200. So 5, I go all the way up to 200 now. Does everyone see how those? Now, I want to make sure I know where they are, so I'm going to draw a circle. I'm going to make sure that I'm not just, I don't want the circle too big, but I want to make sure that I know that those are data points and not just some ink that I got off my pen like I've got down here. All right, let's go on a little further. Let's go up to number 8. So 8 is 275. So I follow this up, and I'm at 200, 225, 250, 275 right there. Okay, let's put a circle around that. And if I go up to, let's see, what was that? That was 8. So 10 is 325. So I follow this up all the way to 300, and there is 325 right there. If I go up to 14, well, let's do 12. So if we do 12, that's 350, although that's not going to be a very good one. Should probably do 13. Well, yeah, I'll do 13. Let's see what was 13. 375. So at 13, I would be at 375, which would be right about there. And then at 14, I'm at 450. So that would be right there. Let's put a couple circles around those so that we know where they are. And let's see if we could lay a straight line. Actually, it seems like we've almost got 2 straight lines here. But I'm going to say that if I laid a straight line to that data, it would look something like that. Okay, now I'm not, that's not the perfect least squares fit probably to that data, but it's a straight line through that data. And we could actually figure out what that straight line is. We can actually take points off it, or I could take points off here. But let's just look at, in fact, it almost goes right from this first point almost to the last point, doesn't it? So that's not far. I'm not far off there. I could actually use this. what I'm going to do is I'm going to say that this point out here is x2, y2. I'm going to say that this point here, I'll use, I guess I could use 1. I'll say this is x1, y1. Does everybody see how I've set those up? And then I also want to choose another color. I don't know, I'm trying some new pens now. I want to find a point sort of right in the middle on there, and I'm going to call that my center point for that distribution. That'll probably throw me off a little bit. I did that a bit different before, but we'll see. I've got a calculator right here, so we can do it. All right, so now, what do we want to do? Let's go back to our sheet of paper. On the semi-log, to find b, log b. And what's the opposite to log? It's 10 to the x, isn't it? Isn't that what you've got on your calculator right now? You've got a log button, and then if you hit the second, it's 10 to the x. So 10 to the x and log are inverse functions of one another, right? Log of 100 is 2. Log of 1,000 is 3. And isn't 1,000 1 times 10 to the 3? Right. See, so everybody knows how these work. Or 10 to the log x equals x2 because they're inverse functions of each other. Does everyone see that? So the way that you would figure out how to do this is to follow this thing that I've got up here. This is for the semi-log, or for the y equals ab to the x. And I know that the NASDAQ is exponential, right? The NASDAQ is an exponential relationship, as I've said about 1,000 times so far. It's exponential, just like the Dow, just like the S&P. They're all percentage-based indexes, so they're all exponential growth factors. Now, just like radioactive decay, population growth, everything else. Okay, so what we've got to do is take log of b, and then we go log of y2. Well, if we look back on our thing here, we'll see that if 14 is my y2, then that would be the log of 450 minus, now let's do it to y1. And if you remember, y1 we said was just 1 and 100, right? So this is 1 100. And this one up here is 14, what was it again? 14 450. Okay, so those are our two. And then this one right in the middle here, why don't I put it right there, and I'll say that that is 7, and if I follow it across, 200. All right, so those are our 3 points that we've got here. I'll just sort of lay this off to the side so you can still see those. So I've got the log of 450 minus the log of 100 divided by, just following this equation we've got up there, by 14 minus 1, right? Okay, so for that, to find out what the log of b is, I've got to take the log of 450 minus the log of 100, and then divide that by 13, and I get 0.0502 5, right? Now that's the log of b. So b then, I'll just put a little thing down here. B equals 10 to the 0.05025, doesn't it? So b equals, let me just do that. That's just going to be 10 to that gives me 1.1226. 1.1226. All right. So that's our B for the NASDAQ index. Now, what's our A? Well, you can see that we can find A by just taking Y divided by B to the X, and I'm going to take the central. So what you want to do is you want to use the central thing for that. And of course, when I look at my central thing, I see that it's 7,200. Oh, here's another question. Where are you going to get this paper? I'll probably send it out to everybody, but you can also go to incompetech.com/graphpaper/logarithmic. Incompetech.com. I have no idea. That's just where I downloaded it, so I thought I'd tell you. You can actually dial up good logarithmic paper there without much problem at all. I also want to show you this paper too, because here we've got a log scale, right? You've got a log scale on the y-axis, but you've also got a log scale on your x-axis. And so this, of course, is called log paper. You're going to plot something off on this too. This log paper, of course, if it's a straight line, always, think of that disclaimer. If it's a straight line, it's a polynomic relationship. And that is, of course, of the y equals ax to the b form, okay? So anyway, we've got b now. Now we want to find a, and you can see a, right, is just going to be y. So let's take a number for y. Well, we've already got the central thing here, 7 and 200. So we're going to say, well, y is 200. And then we need b to the x, don't we? Well, we know what b is. B is going to be 1.1226, and then to the x would be 7. So what is 1.1226 to the 7th, and then take 200 and divide it by that answer, and I get 89.01. Okay, so A is 89.01, so our relationship is going to be y equals 89.01, right, times, I'm going to put parentheses around those, times b to the x, right? Y equals a, b to the x, 1.1226, right, to the x. Now, what if we were looking at y of the year 2020, right? So I'm going to look at y, but with 44, right? X is going to be 44 because it's 44 years from 1976. So if I plug in 1.1226 to the 44th times 89.01, that should tell me what the NASDAQ should be if it hadn't been manipulated by the rich and powerful, rich brokerages stealing the pension funds of us needy baby boomers over the past 20 years. What would it have been had that horrible thing not happened to steal all of our money away? I'm just going to figure it out. Yeah, because since 2000, it's been a totally manipulated stock market. I just want to point it out to you. 1.1226, that's my bias. That's my disclaimer. X to the Y, 44 times 89.01 says 14,434. 14,434. That's what the NASDAQ should be right now. And in fact, we're not all that far off from that with all the bumpy road and everything that we've been on for the past several years, are we? Now here's what I want you to do. I want you to write down all of these. I'm going to go through them. 1, 9, 2, 11, 3, 14, 4, 17, 5, 21, 10, 65, 20, 607, 28, 36, 18, 30, 56, 55, 50, 490,454. You won't have to plot that, I don't think. 134 billion. So you won't have to plot those two, but you'll have to plot, you know, the rest of these. Now, with this exponential, remember, along the x-axis, you don't have to plot all of those, of course. I would say only plot up to maybe, you know, 28, because you've got 28 divisions on that sheet of graph paper that I'm going to send you out for lab 2, right? This graph paper that I've got right here in front of me. And then for this one over here, you're going to have to probably start at 0.1. 0.1 to 10, or 0.1 to 1, 1 to 10, 10 to 100. Yeah, that'll do it. 0.1 to 1, 1 to 10. This is the x-axis, remember. 10 to 100. This is with the log paper. And down here, remember, your equation to figure out what b is different than up here in the semi-log. The log is for polynomic, right? Let's write that in there again. Log is for polynomic relationships, right? And that should be a giveaway because it's got ax to the b. And this is for exponential, like we did in the example I just gave you, right? So this is for polynomic. This is for exponential. I've written polynomic and exponential over here in the two data sets that you have to plot out. You have to plot those out, and you have to give me an equation. So what I want is this sheet of paper with your things drawn on it, right? And an equation for what the line is going to be. So you basically have to plot those out just like I plotted this out. You know, make your straight line, make a decision on what you're going to choose, and then, and by the way, these two data sets are almost perfect straight lines on log and semi-log paper, respectively. All right, does everybody see that? Okay, good. So I'm going to send you out some graph paper to do those on, and you do those and send them to me for lab 2. Okay. I'm going to put this one up on the YouTube channel for you to watch.